Hey everyone, and welcome. Today we're going to dive into what is basically the secret code of the universe. Seriously, it's the mathematical language that describes pretty much everything that changes, moves, grows, or decays. We are talking about differential equations.
I mean, that's the big question, isn't it? How can we possibly use math to predict something? Whether it's the orbit of a planet, how a disease might spread, or even just the vibration of a guitar string. How do we model that kind of stuff, let alone predict it?
Well, the answer is actually pretty elegant. We do it by getting a handle on the rules of change itself. See, once you know how something is changing at any single moment, you can basically trace its entire story, both into the past and into the future.
So, here's our game plan for today. We'll start with the big idea of change itself. Then we'll decode what a differential equation actually is. We're going to look at the two main flavors they come in, introduce a really powerful shortcut for solving them, and then finally, see how all this math is literally shaping the world around us.
All right, let's start at the beginning. The universe isn't just sitting still, right? It's in constant motion, always in flux. And for centuries, the huge challenge for scientists and mathematicians was figuring out how to describe all that movement with any kind of precision. And when we say change, we mean everything. It's your coffee getting cold. It's a population of bacteria growing. It's a planet swinging around the sun. All of these are just systems that are varying over time or space, and believe it or not, they all follow a specific set of mathematical rules.
And that brings us to the tool we use to actually write down those rules. The best way to think about a differential equation is not as some scary, complicated formula, but more like a recipe that tells you exactly how a system is behaving right now at this very instant.
Okay, so here's the key takeaway. A differential equation doesn't just tell you the value of something, like the temperature of your coffee. No. Instead, it describes the relationship between that temperature and how fast it's changing. It connects a function to its own derivatives, its own rates of change. And this right here, this slide shows the fundamental shift in thinking. You know, with basic algebra, like x plus 2 equals 5, you're just hunting for a single static number. Easy enough. But with a differential equation, you're solving for a whole dynamic story, a function, a pattern, a curve that describes behavior through time. It's a much bigger prize.
But, not all change is created equal. Sometimes you're just tracking one thing changing over time, but other times you're tracking lots of things changing all at once. And that simple difference gives us the two major families of differential equations.
So on one side, you have ordinary differential equations, or ODEs. These are your go-to when a problem depends on just one single variable, usually time. Think about a pendulum swinging back and forth. Perfect for an ODE. On the other side, you've got the heavy hitters, partial differential equations, or PDEs. These beasts tackle the complex stuff, where change depends on multiple variables, like how heat flows across a metal plate. That changes over both time and location on the plate.
So a really simple way to picture it is like this. An ODE is tracking a single car driving down the highway. It follows that one path, that one journey through time. A PDE, though, that's not just one car. It's like a satellite image of the entire city's traffic grid. It's not just one path. It's mapping out a whole landscape of change, showing you what's happening everywhere, all at once.
Okay, as you can imagine, actually solving these equations, especially those big PDE landscapes, can get ridiculously hard. So what do mathematicians and engineers do when they hit a wall? Well, they invent a brilliant shortcut.
I mean, seriously, you're staring at these incredibly tangled relationships with rates of change and rates of change of rates of change. How on earth do you even begin to unravel that knot?
Well, you don't. You translate the problem into a completely different language, a language where it's way, way easier to solve. And one of the most powerful translators ever invented for this job is the Laplace transform.
And this process right here, it's just so clever. You start with your nasty calculus problem. Then you apply the Laplace transform, which translates it into a much friendlier algebra problem. You solve the easy algebra, which is a breeze, and then you use the inverse Laplace transform to translate the answer right back into the original language. It's this beautiful little detour that lets you sidestep all the hardest parts of the math. So what makes it so dang powerful? Well, for starters, it turns the hardest part of calculus, derivatives, into simple multiplication. It's like magic. It's also amazing at handling sudden, sharp events. Things like flipping a switch on. That's what engineers call a unit step.
or the instant impact of a hammer blow, something called a Dirac delta function. It just handles them, no problem. Plus, it has other powerful tools built in, and maybe best of all, it automatically bakes your starting conditions right into the problem from the get-go. It's an incredible toolkit.
Okay, this is all fascinating theory, but let's zoom out. What's the payoff? Why does any of this matter in the real world? Well, it turns out this mathematical engine is running silently in the background of just about every piece of modern technology you can think of.
Seriously, it is everywhere. It's used to design the circuits in your phone. It models the air flowing over the wing of a plane. It helps epidemiologists predict how diseases will spread. It's in financial markets, engine design, making sure bridges don't collapse. It's even at the very foundation of reality in quantum mechanics. This isn't just abstract math. It's the blueprint for our world. And it really brings you back to this timeless quote from Galileo. Mathematics isn't just some abstract game we invented. It feels more like we discovered the language that nature itself is written in, the language we use to understand how the universe actually works.
So when you boil it all down, differential equations and these incredible tools like the Laplace transform, they're not just something for a textbook. They are the invisible architecture, the hidden operating system that makes our entire technological society run.
Which leaves me with one final question for you. Now that you have a little glimpse into this language of change, if you could use it to model and predict anything, what would it be? What pattern in the world would you want to finally understand? Something to think about. Thanks so much for joining me.